Hi everyone, my name is Chelsea Mackaman-Lofland, and I'm a scientist in residence and geology graduate student at the University of Texas at Austin. I study the rock record to better understand how forces in the earth cause mountain ranges to grow and evolve. And as an earth scientist, I've been able to travel all over the world to solve problems and do research. This photo was taken where I've done most of my studies in the Andes Mountains of South America. But in addition to these opportunities to work in gorgeous places, geoscientists study mountain building because major global mountain ranges, such as the Rockies, Andes, Alps, and Himalayas, are fundamentally linked to Earth systems, including the formation and evolution of continents and oceans, to climate and weather patterns, and to the distribution of natural hazards and resources. Given these direct impacts on Earth systems and human society, we want to understand how do mountains form. Earth is covered by a thin skin of solid crust and uppermost mantle called the lithosphere, which is broken up into interconnected pieces called tectonic plates. These rigid pieces float atop the more dense, semi-molten asthenosphere, which is shown in red on this 3D diagram that illustrates the surface of the Earth and the processes operating underneath. There are two basic types of lithosphere: oceanic, which is relatively thin and dense, and continental, which is thicker and more buoyant. Convection currents, due to temperature differences within the Earth, as well as density contrast between the pieces of lithosphere and the underlying asthenosphere, has oceanic and continental plates to move and interact, controlling the evolution of Earth's surface. For example, new oceanic lithosphere is created where plates pull apart at divergent plate margins. While oceanic lithosphere is consumed, and earthquakes, volcanoes, and mountains occur at convergent margins, so where plates smush together. This map shows all of Earth's oceanic and continental plates, which fit together like a giant global puzzle. And the black and red lines show places where the plates are converging or crashing together. When we compare these plate boundaries with global topography, we see that most mountain ranges occur along these convergent tectonic margins. As I mentioned earlier, my research at UT focuses on the Andes Mountains, where parts of the Pacific Oceanic Plate are being consumed beneath the South American continent. And I want to understand how and when this plate convergence started and how the Andes Mountains began to grow and evolve. This mountain building started many millions of years ago, so we have to do a bit of detective work to reconstruct what happened that far back in time. In geoscience, that detective work involves studying the records of past Earth environments preserved in the rocks. As mountains are uplifted, they're also eroded by glaciers, rivers, and streams, and the material that gets shed off the mountains is accumulated in sedimentary basins, which are shown in yellow on this diagram on the left. The photo on the right shows such a basin, which contains a several-mile-thick pile of material or sediment that was eroded off the growing Andes Mountains over the course of millions and millions of years. Different parts of the Andes are made up of different rocks, so when they're eroded, they deliver different types of sand grains to the basin. We also know that older sediment fills the bottom of the basin, while younger material is at the top. By looking at the different types of sand grains in the basin sediments, and identifying changes in sand grain or rock composition through time, we can figure out when different ranges in the Andes were uplifted and eroded, just like detectives using different clues or pieces of evidence to resolve a case. In this basin, we can tie the sand grains preserved in the lowest, oldest part of the basin to mountains in the western part of the Andes. Ancient river sediments from the middle part of the basin contain sand grains derived from the central part of the range. And sand grains from the youngest, uppermost part of the basin were derived from the ranges at the eastern Andean flank. Fossil or radiometric ages from the basin rocks give us additional information about when different materials were eroded and accumulated. And we can use this evidence to piece together what we think the Andes looked like through time. So here that involved initial uplift of the western Andes, and then erosion and sediment accumulation in the basin, followed by uplift and erosion of the central part of the range, and finally uplift of the range of the eastern Andean flank with ongoing erosion and accumulation in the basin. And this gives us a better idea of how the Andes here grew and evolved, and is one example of how I use the sedimentary record preserved in basins to understand mountains. Again, my name is Chelsea. Thank you for listening.